So good morning. Welcome. My name's Brad Calder. I'm a director and architect of Windows Azure Storage. And before we get into some storage details, I first want to spend a couple slides talking about Windows Azure and the Azure platform. So we released as a CTP a few months ago at PDC, Windows Azure. So you can go to our website, download those bits, and start playing with it today if you want. And what Windows Azure is basically the foundation of Microsoft's cloud platform. You can think of it as an operating system in the cloud that provides essential services for the cloud, such as virtualized computation, scalable storage, automatic management, and a rich developer SDK. Now, you might have seen this slide here, which sort of gives a picture of the services that are part of the overall Azure platform. And as you can see, Windows Azure is sort of the foundation of that, providing this operating system for the cloud. Now, the thing I want to point out on this slide is that there's actually two storage offerings with the overall Azure platform: Windows Azure Storage as well as SQL Data Services. SQL Data Services is focused on providing scalable relational database service in the cloud and exposing SQL to the cloud. And what Windows Azure is focused on providing, since it's the operating system for the cloud, it focuses on providing some essential storage solutions that an operating system would normally provide. And this talk is on Windows Azure Storage, and there'll be a talk on SQL Data Services tomorrow in this room at 9 a.m. Okay. Now, what's the focus and the goal of Windows Azure Storage? Well, the goal is to allow users and developers to take advantage of the vast amount of storage that exists in the cloud. Now, with this storage, you can create applications that allow you to access your data from anywhere at any time, scale to store data for any length of time, scale to store any amount of data, be confident that data will not be lost, and basically pay for this as a utility-based service, which is very important because you don't have to over-provision for peak capacity. Now, what our storage solution provides is a durable, scalable, highly available storage solution in the cloud with rich storage concepts. The three storage concepts we provide right now with the CTP are blobs, tables, and queues. With blobs, you can actually store and access large data items in the cloud. Tables allow you to manipulate your service state in the cloud and query over that service state. Queues allow reliable delivery of messages for your application. And these are provided with very simple and easy to use programming interfaces. Everything is REST accessible with HTTP and HTTPS, as well as .NET accessible. Now, in order to actually use the storage system, the first thing you need to do is go to our web portal. And when you log into the portal, you can create a storage account. When you create a storage account, you create a globally unique account name that represents you to us as a service. And you get back a 256-bit secret key. You then use that secret key to authenticate all your requests to our storage system. You basically take the request URL, the request header, you canonicalize that with the secret key, you get back a signature, then you pass to the storage solution, our storage server, the signature along with your request, and then we authenticate it at our store. Okay? Now, one thing we just announced yesterday at PDC is that we have a new feature, which we call geolocation and co-location of storage and computation. So what this is going to allow you to do is you can go to the portal, and with your storage account, you can specify, I would like my storage located in, let's say, US Northwest or US Southwest. You specify a geolocation, and your storage is basically located there and replicated there. Now, we'll be adding additional geolocations over time. We're probably going to start out with, I think, with the US Northwest and US Southwest, but we'll have geolocations in Europe, Asia, et cetera, over time. Now, one other exciting thing you can do with this is you can actually specify the co-location of your computation with your storage. So you can say, I would like my storage account and my computation account to be affinitized and then to be co-located in a geolocation. So this means that you can actually have your virtualized computation running right next to your storage for high connectivity. And this will be coming, I think, at the end of April. I think that was announced yesterday. Now, once you have your storage account, you can then access our three fundamental storage abstractions: blobs, tables, and queues. As I mentioned, blobs provide a simple interface for dealing with large objects and files in the cloud. Tables provide the ability to deal with structured storage, where a table is a set of entities, and entities are a set of properties, and you can query over any entity and property. And queues provide this reliable delivery of messages for your application. And I'm going to go through each of these in detail, starting with the blobs. So shown here are the blob storage concepts, where you have your storage account that you created in the portal. With that, you can create one-to-many blob containers, and then you store your blobs in these containers. So take this example up here where we have Sally. She wants to store some pictures and movies in the cloud. So she creates a pictures container and a movies container. And in her pictures container, she stores image 1, image 2. And in her movies container, she stores this movie 1. Okay? And let's go through these three concepts in more detail. So as I mentioned, with a storage account, you can create many blob containers. And you can think of the blob container as a way of grouping together your blobs. It's basically a container is a set or collection of blobs. And you can do a few things at the container level. You can set sharing policies on your container. You can set that all the blobs in this container are to be publicly accessible or private. So for example, if Sally makes her pictures container public, then anybody who knows the URL to that image 1 and image 2 on the prior slide can get access to it by just specifying the URL. If the container is private, then only an authenticated access can get access to those blobs. So you can basically set the sharing policies of the blobs, all the blobs in a container at the container level. Now, you can also associate metadata with the container. You can associate name value pairs up to 8 KB. So going back to our example, if Sally wants to associate metadata with her pictures container to keep track of, for example, who the photographer was, she can associate that at the container level. And finally, we provide some rich data abstractions for listing over blobs in your container. And I won't go into the details of that, but there's details online. So now that we described a storage account and container, let's go through what it actually looks like accessing one of these with the URL. So shown here is a standard blob URL, where the first part of the URL for a standard access is your storage account. You then specify the keyword blob, which indicates to us that you want to access the blob store, corewindows.net, your container name. And note the container name cannot have any forward slashes in it. So everything after the next forward slash will be the blob name. So going through another example here, if Sally wants to host a container of music in the cloud, she would create a container called music. And then let's say she wants to organize that music by the type of music, name of the band, and the song. And she can do this, and she can use the forward slash here as a delimiter to do some interesting list operations over that hierarchy. And I won't go into the details of that, but we have examples online. Now, with this blob and container she just created, she can then use this URL that's shown here to put and get this blob from our store. Okay. Now, for the blob features and the functionality of our REST interface, for the CTP, we support up to 50 gigabyte blobs. And you can also associate metadata at the blob level, just like we talked about with the containers. So if I want to associate with my pictures, who's in the picture or what date the picture was taken, you can associate that metadata with the blob. And you can set and get that metadata separately from the blob. Then for the REST interface, we provide a standard REST interface where you can put a blob, get a blob, delete a blob. Put blob, the semantics right now is basically it inserts a new blob into the store or overwrites that existing blob there. Get blob, you can get the whole blob or get a subrange of the blob and, of course, delete a blob. So let's go through two REST examples of putting in and getting the blob. So assume we're a DVD content provider and we want to store some movies up in the cloud for streaming. So we may create a container called movies, and let's put the blob movie up into the cloud so that we can download it later. So this is what the URL for the put would look like, where we specify DVD blob corewindows.net, the container movies, and the name of the blob, the blob. So the next thing you would specify as part of your URL request is the header is the content length of the blob, the content type, maybe some metadata you want to associate with the blob, such as what year was the movie filmed, and a tagline, beware of the blob. A content MD5, and this content MD5 actually represents the MD5 of the blob data bits. And we'll check that when you upload it into the cloud. And you can also get this MD5 back when you download the blob, so you can actually check it when you retrieve the whole blob. You specify the data of the request, and then the signature I talked about on the prior slide. And finally, the blob data bits. And that's all it is, all that you need to do in order to upload this blob up into the cloud. Now, if you want to get the blob, you can actually get the blob with using just this URL if the movie's container is marked as public. So if all the blobs in the movie's container is marked as publicly accessible, all you need to do is do this standard URL get, and you can then start streaming down the movie and start watching it. If you want it to be a private access, you would then have to also specify a signature as well as the date and time. Now, let's say you actually wanted to just get a sub-range of the blob movie. You can do that by doing a range get here. Maybe this is your favorite part of the movie. And for authenticated range get, you'd also have to specify the authorization, which I didn't show. OK, now if you're doing one of these large puts up into the cloud, especially a multi-gigabyte blob, that can have some severe performance effects if you get a connection error. If you've already uploaded 10 gigabytes of a blob and you still have a few more gigabytes to go, you get a connection failure, well, you'd have to reload the whole blob up into the store. So we wanted to address this by actually adding a new storage concept to the blobs, which we call blocks. So what you can do is you can actually upload a blob via blocks, then commit those blocks to be the readable version of the blob. So showing here, we can actually upload block 1, block 2, block 3, and then we can commit these to be the readable version of this movie 1. And then you can do a standard get blob to actually download and read that movie. Now what this means for our storage offering is we offer two ways to upload a blob. You can do a standard put blob, or you can do these put blocks, commit the blocks, and then you can get the blob just using the standard get blob interface. So there's only one way to get a blob, which is via get, and you get it at the account container blob name. And so you can get image 1, image 2, as well as the movie with the standard get. So the get doesn't deal at all with blocks. So let's go through some examples in a little bit more detail. So we want to upload this 10 gigabyte movie into the cloud. We want to upload the movie, The Blob. So we first define the name of the movie, The Blob. And to upload this via blocks, the first thing we do is we take this 10 gigabyte movie and we break it up into what we call blocks. Each block has a unique ID scoped by the blob name. And then we just do standard puts to upload each of these blocks up into this cloud. So we do a put of a put block ID 1, then a put block ID 2. And the nice thing about this is if you do a put block and that put block fails, you can retry that put block and then continue where you left off. They eventually upload all the blocks up in the cloud. And note these blocks are actually associated specifically with that blob name, and only that blob name. Now once you've uploaded all these blocks up into the cloud, you then do what's called a put of a block list. And this effectively commits a list of blocks to be the readable version of the blob. So shown here is we do a put block list based upon with this list of blocks from 1 to n. And once we do this, we now have a readable version of the blob movie in the cloud consisting of those blocks in that order that we could then download with a get. Okay? Now, the few benefits for this is that, as I mentioned, you get efficient continuation on retry, meaning that if you upload a block and you get a failure, you know that you need to re-upload that block and you continue where you left off. It also allows you to upload blocks out of order or even in parallel. And then what matters there is that block list. That order of the blocks in that block list will be the readable version of the blob. So let me go through this in just a little bit more detail. So in this example, I'm going to upload an example blob. And I want to demonstrate three things. Uploading blocks out of order, uploading blocks with the same ID, and uploading unused blocks. And what are the effects for those? So I'm going to upload to this example block the following 5 blocks in this order. We're going to do a put block of block ID 1, put block of block ID 3. And remember, when you put a block, it's associated and basically scoped by that blob name and just that blob name. Put block of a block ID 4, then 2. Now, let's assume that we never got an ACK back for a put block ID 4, so we need to upload it again just to make sure. Okay, so we upload block ID 4 again. Now, in this example, I want to create a readable version of that blob that consists of block ID 2, block ID 3, block ID 4 in that order. And when I do this put block list, what will happen is the system will take these 3 blocks and create this readable version of the blob. So if I did a get blob with this example blob, I would see the blocks in the following order. All the data for block ID 2, then 3, then 4, doing the standard get. Okay? Now, this shows the first thing I wanted to demonstrate, which was what really matters is the blocks can be uploaded out of order, and what matters is the order of the blocks in this block ID list. That's the commit order to represent the readable version of the blob. The other thing to demonstrate here is that we actually uploaded blocks with the same ID twice, block ID 4. Okay? And what the semantics of that are the last block ID uploaded before a put block list, that will be the block used and consumed in the new readable version of the blob. And finally, we have a few blocks here that we didn't end up using. What happens to those? Well, when you do a put block list, all the blocks that were left over are basically deleted. Okay? So if we actually wanted to use that block ID 1 in a later put block list for this blob, we would have to reload it up into the cloud. And that's the semantics we have right now for the CTP. So let's go into some details for blocks. Actually, under the covers for our blobs, every blob is a list of blocks. So a blob can be up to 4 megabytes in size. The blocks can be up to 4 megabytes in size. The blocks can be a variable size. So all the blocks that you use to commit a blob, they can actually be of different size. And each block has a unique block ID scoped by the blob name, as I've described. Now, to upload the blocks, you just do a standard put of a block. And this puts the block as an uncommitted block associated with this blob. So you have this blob foo that you're uploading this block for. It sits there associated with this blob until you actually do a block list commit. Now, note that this block will sit here as an uncommitted blob, and you can't actually read the contents. You can't actually get to that contents that you've uploaded until you've actually done the put block list to create a new readable version of the blob. Then, as I've described, to actually commit the list of blocks, you use a put block list. This takes a list of uncommitted blocks that you've specified, commits that to be a new readable version of the blob, and then the remaining blocks are basically thrown away. And finally, we have another block list function you can use is once you have a committed blob that was uploaded via blocks, you can actually download the original block list you used to commit the blob. And when you download that list, you're not really downloading the blob contents, you're just downloading the block IDs along with the block sizes. And I'll go through an example in a few slides of how that's useful. So to wrap up the blob section, I want to talk about 2 things. Blob concurrency, as well as how to choose a block ID, and some interesting things there. So there's 2 types of concurrency I want to talk about. The first one is what happens if you have an overlapping get with a put. So let's say I started a get, and I'm downloading this long, multi-gigabyte file, so it's going to take a little bit. I then come in and do a put on that same blob name. Well, what happens? Well, the semantics that we guarantee is that you will always, when you do a get, you will always see a single version of the blob. So you'll basically think of this as a sort of snapshot semantics. And that if I downloaded this get, I started this get, another put comes in to basically overwrite that blob. As that get completes, I'll see the prior version of the blob. Now, one thing to realize about our storage system is that we only maintain in our index the recent puts for a blob. So if I have another get come in after I've done that put, it'll see the new version of the blob. Now, why is that interesting? Well, if you're downloading this long get, and let's say you get a connection failure, and somebody else had come in and overwrote that blob in the meantime, when you issue the new get, you would actually see the new blob. And the one way to basically deal with that semantic-wise is you can do a conditional get based upon the E tag. So when you did the original get, you get back this E tag. Okay? If you actually get a connection failure partway through that get, the good thing to do for your application is to continue the get by doing a range get for the rest of the blob. And you probably want to do a conditional get specifying that E tag so that you can be notified if it's changed since you did the original get. And then your program can deal with those semantics however you want. Now, the next thing I want to talk about is concurrency, is multiple clients trying to write the same blob. Okay? So if you have multiple clients trying to put blocks up into a blob, so they're putting these blocks, these two clients are putting these blocks up here. What happens is that the first client that actually does a successful put block list will create the new readable version of the blob, and all those other blocks will be deleted, as I described earlier. So if client 1 does the put block list first, then they'll get a readable version of the blob with their blocks. Then client 2, when he does a put block list, he'll realize some of my blocks are missing. So I need to re-upload those blocks and then do my commit. Now, one important feature that we provide for dealing with concurrency for blob puts is a conditional blob put for optimistic concurrency. So if you have two clients that download a blob, they then update the contents, and then they want to upload that same blob, you probably want to do a conditional put on the E tag that you downloaded to make sure that it's the same as when you do the put, to make sure that you're not overwriting a change that somebody came in since you actually did the get. So this is a nice way of providing optimistic concurrency for your concurrent blob updates. Okay, the last thing I'd like to talk about for blobs is choosing the block ID. Now, the block ID actually represents the 64 bytes of metadata that you can actually track for a blob. So you can put whatever you want in there, okay, and track whatever you want at the block level. Now, one interesting thing that some people are doing with this is the following. Now, going back to our example for concurrent blob updates, you have to deal with this fact that if you have two clients trying to update the same blob, you could have block ID name collisions. And if that happens, as I described earlier, the last block uploaded before the put block list will become part of the readable version of the blob. So yeah, you could have clients that basically will always have a different namespace for their block IDs, and that's great. But if you want another way to deal with this is to actually make the block ID to be a unique hash of the data block contents. And so if you have two clients uploading the same block ID, well, that means they're actually uploading the same block and everything is fine. Now, in using the same context, you can actually use the block ID represented by a unique hash to do data integrity checks for range gets. One common request is, I want to do a range get, and I want to do MD5 checks on those ranges. Well, if you've actually uploaded your blob and actually specified as the block ID, the block IDs, the unique hash or the MD5 or whatever you want of those blocks, before you actually download your range gets, you could do the get block list. And with the get block list, you get the list of all the blocks with their block IDs and size, so that when you do the get blob ranges, you can actually do your data integrity checks over those different ranges, using the block IDs to do the data integrity checks. So in summary, for Windows Azure blobs, we provide an easy-to-use REST put get delete interface. You could do a get of the whole blob, or for ranges. You can do this conditional put and get to efficiently deal with concurrency. And the blocks provide an efficient way of dealing with continuation on uploading of a blob, as well as having this metadata that you can associate with the different block IDs. Now, for our CTP, we support up to 50 gigabytes per blob using a put block and put block list. If you just do a single put blob, we support up to 64 megabytes. We're thinking about increasing that limit, but we really want to encourage people to use the blocks if you're uploading very large blobs. And we do have some future features coming in this area: copy blob, update blob, and append blob. Especially like for update blob, we want to make it possible for you to only have to upload the blocks that you actually want to modify for your blob. So you don't have to upload all the blocks each time you want to update a blob. So I'm going to move on now to talk about tables. I think questions are at the end. So for tables, we have Windows Azure tables provide structured storage for the cloud. And the goal here is to provide access to massively scalable tables where you have a table of billions of rows or terabytes of data. And this automatically scales to your table across our servers to meet the traffic demands for your application. These tables are highly available, durable, and we provide them with a familiar and easy to use programming interfaces via ADO.NET data services. So you can use Link with .NET classes to access your tables, or REST to access the tables with any other, basically with any platform or language. Okay, so shown here are the data storage concepts for tables, where with your storage account, you can create many tables. And inside your tables, you actually store these entities. So going back to our storage account, Sally, let's assume that she wants to have a table of users and a table of photos. So she creates a table called user and a table called photos. And inside her user table, she stores these entities. And the properties, let's say she wants to keep track of, are the name of the user, the email address, and for the photos, she keeps track of a photo ID and a date. Okay? So let's go through these concepts in more detail. So as I mentioned, with your storage account, you create your table names, and the table names are scoped by that storage account. A table consists of a set of entities, and you can think of each entity as basically a row in your table. And each entity contains a set of properties, and you can think of these properties as basically columns. And every entity has two unique keys, which are basically a partition key and row key. And these together represent the primary key for your table. So let's go into detail first on what exactly is a partition key. Okay? Well, every table has a column which we call the partition key column. And you can sort of think of it as the first column of your table. Now, we use this partition key to basically group your entities into what we call partitions. So all the entities with the same partition key value are grouped into the same partition. And we do this so that we can monitor those partitions and then load balance them across our servers. So a table partition are all the entities in the table with the same partition key value. And we expose this to the programmer in the programming model to allow the application to control the granularity of their partitions and to enable scalability. So let's go through an example. Here we have an example table where it's a document versioning table where every entity or row represents a different version of a document. And the two documents we're tracking here are the example document and the FAQ document. Okay, and for the properties or the columns, we have the document name, the version, modification time, and the description. Now, as I described earlier, the first column here is the partition key. So this partition key groups these different entities into the following two partitions. We have a partition represent all the versions of example document and a partition representing all the versions of the FAQ document. Okay? And as you can see, the row key is used to uniquely identify each entity within the partition. Now, what this partition allows us to do is that now we have two partitions. If your table gets too much traffic to be served by one storage server, well, we can take these two partitions and then put them on two different storage servers. And then we always keep a partition basically accessible from a single storage server for the way we do our transactions. Okay? So the more partitioning you have in your table, the easier it is for us to spread your table out across our servers to meet your table's peak performance needs. Well, let's go through what the purpose of this partition key is. Well, the first thing it allows you to do for your application is to reason about what we call entity locality. Basically, all the entities in the same partition will be stored together so you can get more efficient querying over them as well as cache locality. But the two main reasons why we provide this are as follows. Entity group transactions. This is a future feature we have coming. What this provides is the ability to do multiple entity operations all in one atomic transaction to the storage system. So you can do multiple insert, updates, or deletes over multiple entities as long as they're within the same partition, which means that all those entities have the same partition key value. Then the other big reason why we have the partition key is that this is our level in which we basically scale your table out over our servers. So we monitor your different partitions in your table, and the traffic to those different partitions. And if a given server is getting too hot, we'll take those partitions and we'll load balance them over more storage nodes to basically serve the traffic needs for that table. Well, one common question we get is, well, how do I actually choose a partition key? And there's sort of two things you want to trade off here. One is the granularity of choosing the partition key so that you can probably benefit from this future entity group transactions feature we have. And the other thing you want to trade off is having enough partitions so that we can load balance your table across our storage nodes. So at one extreme, you can put everything into one partition in one table. And that allows you to do atomic transactions once we have that feature across all those entities. But that really doesn't give us any opportunity to basically spread your table out across different servers. At the other extreme, you can actually have every single entity could have a different partition key. And this gives us a lot of opportunities to basically spread your table out. Now, just to give an example of sort of a nice partitioning for a common database example is take a customer's table. A customer's table might have a set of orders, and an order might contain a set of details. Now, if you want to do atomic transactions across those three different types of entities, you may want to partition them so that the partition key is the customer ID. Okay? You still have the row key to basically uniquely identify the different entities and the different components, but this will basically group those different entities for a customer into the same partition. So one, you get efficient querying over them, but you also can do atomic transactions over them once we have entity group transactions. Then in terms of scalability, well, the partition key in that example is a customer ID. Well, assuming you have thousands or millions of customers, that gives us a lot of opportunity to basically spread your table out across our servers. Now, one thing you need to keep in mind, at least for using Windows Azure tables at this time, is that we do only provide one primary index. What that means is we provide a primary index sorted by the partition key and row key. Okay? A future feature we have coming is secondary indexes. And what this will provide is the ability to actually have different sort orders on non-key properties, as well as the ability to do efficient querying on non-key property indexes. But for now, for the CTP, we only have one primary index. So given that, it's very important that you choose your partition key to be part of your dominant queries. So if the partition key is part of your dominant queries, what that means is when you do your query, you'll go to that partition server, find your results, and then come back. If the partition key is not part of your query expression, you basically will have to actually scan over the different partitions. You can do that and get the query back. It just won't be as efficient. But once we have secondary indices, those non-key queries will be more efficient. Okay. So in going into the details for table entities and properties, as I've described, the two mandatory properties for every table are the partition key and the row key. And internally, we also have another property which keeps track of the version of each entity. And this is used to provide optimistic concurrency under the covers. Now, each entity can have up to 255 properties. And one of the unique things about our table is that there's actually no enforced schema other than this partition key and row key. So all the other properties can be whatever type you want, any of these .NET types down here. And the properties are actually stored as name type value pairs. Okay? So you could actually have two entities that even have different properties. And as I described with the customer orders example, you could actually even put into a table different types of entities. Okay? And that's because we don't enforce a fixed schema, which can be actually very useful, which I'll get into an example in a few slides. Now, for the programming model, we wanted to leverage your .NET expertise. So we went with the ADO.NET Data Services release of Astoria as a programming model for Windows Azure tables. So you can access your tables via link or via the RESTful interface ADO.NET provides. And you can do inserts, update, deletes over your entities, and you can query over the tables. And when you query over the tables, you get back a list of structured entities. So now I want to go through just a few slides giving a sort of example of using the table system with ADO.NET. So going back to this customer example, Let's assume we have a table of customers that we want to store entities up into the cloud. And we want to do this with ADO.NET Data Services. So the first thing we do is we want to create a class to represent our entities that we're going to store into our table. So we have a class called customer here. And the first two keys that we're going to provide, the first two properties we're going to define are the mandatory partition key and row key. Where here the partition key is going to represent the customer last name, and the row key is going to represent the customer first name. And then let's add some additional properties we want to store for every customer. In this example, how long has the customer been a member of our service, the rating of the customer, and its occupation. Now, there's one additional thing we need to do in order to hook this class up into ADO.NET Data Services. We need to specify a data service key annotation. And what this does is specifies for this entity class what are the primary keys for this entity. And that's the partition key and the row key combined. Okay. Now, once we have this class, we can now start storing these entities up into our table. Now, there's one step I'm skipping over just due to time is if you want to use the customer table, the first thing you would do is you register the customer table name with your storage account in the cloud. It's a very standard process, very simple to do. There's examples for that on the web. So assuming that we've registered that customer table name with your storage account, you can then start inserting customers into that table. So let's just go through an example for that. So here we create a customer called Getty Lee, who's an engineer. And in order to actually access the storage, the Windows Azure table storage in the cloud, the first thing you need to do is create a data service context for ADO.NET. So we're going to specify the URL for accessing the structured storage. This is the URL you would use if you were to use the REST interface to access the structured storage. So it would specify your storage account, table, core-windows.net. You then pass this string into the ADO.NET data service context provider, and it provides a context object. You then use this context object to perform all of your requests to the cloud. And it knows what storage account you're accessing because you've already specified it in this service URL. Okay, so now let's add this customer to our customer table. So that's shown here, where we say add object to our data context object, where we're going to add our customer into the customer table. So this string is actually the table name that we registered earlier, which I described verbally. Now, this basically associates that customer object with this data object, this context object. Then once you do save changes, this will actually push this change to the store in the cloud, and it will insert this customer entity into your storage account specified by the service URL and to the table specified here when you did the add object. Okay? So once you've done this, this entity has been put up into the store. And it's really just that simple to basically start using Windows Azure tables. Now, the exact same sort of example holds for updating an entity and deleting an entity. Is very simple to do. I don't have time to go through that, but we have examples online. The last thing I want to show with this example is really just querying over our table. And so let's start off doing that with link. Again, we need to have a data context object defined. And that's here. We're going to pass in our storage account so that when we do operations on that data context, it knows what storage account we're accessing. In our link query, we're going to specify the entity class and the table that we're going to access. So customer in quotes is the table we're accessing. And that's going to return back a set of customer entities. And then we can do a filter on this query where we're going to look for all the entities that have the partition key equal to Lee. So once we formed our query, we can then go to the for each statement, which will execute the query to the cloud. It'll look in the customer table in our storage account for all of the entities where partition key equals to Lee. It will return those entities as objects, which you can then traverse over and do whatever you want with. Okay? Now, I also want to give just a slight taste of using this interface with REST. And that's shown here. So with REST, you would just do a standard GET, where you specify my account, your account name, table, core windows.net. You then specify the table name, and then the where clause, basically the filter query. And that's basically as simple as it is to basically do the query in REST. And note that this example focuses on querying over the partition key, but you can actually query over any property in your table, not just the primary keys. So in wrapping up the table section, I want to go through a few tips. I'll first start off by doing a few tips on using few performance tips for .NET and ADO.NET. We just posted on our forums today more details and examples for these tips here. So if you want more details, please go to the forums and see the post that was put there this morning. So the first thing I just want to briefly talk about is when you're using .NET, by default, you get 2 connections. Okay? So if you actually want to do more than 2 concurrent transactions to Windows Azure tables, you need to increase the default connection limit to whatever you want it to be. So that's the first thing to mention. The next is, by default, ADO.NET or .NET basically sends up a post request with a 100 continue. What that means is that it will send just the header with a 100 continue. On the server, we will authenticate the request, assuming that it's correct. It will then go back to get the rest of the payload. Okay? Well, if you're doing small transactions, that can actually take a lot of additional overhead because you're doing this extra round trip. So if you know that your authentication will typically work and you've tested your application well, you probably want to set the expect 100 continue to false so you can actually save this 1 round trip. The next thing I want to mention is change tracking. Now, when you do a query, if you're going to actually modify those objects and put those changes back up in the cloud, you want the change tracking on in ADO.NET. But if you do a query and you actually aren't going to change those objects, you may want to turn change tracking off for that query, because that will just avoid the additional overhead with ADO.NET doing its change tracking. And finally, there is a performance bug in ADO.NET in its deserialization right now, and they're working on fixing that. So if you experience this issue, what it means is your queries could take 5 or 10 times longer than they actually should. So there's 2 workarounds for that. One is, if you actually name your entity class for your table the same as your table name, then this will work around the issue. So in my example, I had a table called customer, but the class I also had was also called customer, and that works around this issue. If I actually had called the customer table, let's say customer table, and then the class called customer, you would have seen this performance issue. The other way to work around this is actually to define the resolve type yourself when you actually resolve the entities. And you can actually override that with a resolve type. And there's an example for that in the forum that was posted this morning. So if you're using .NET and ADO.NET to access Windows Azure tables, you do want to try to look at these 4 performance tips and make sure you're getting the best out of our system. Now, a couple tips in terms of tables I want to talk about is, one, when you do a query, you get 60 seconds on our server to complete the query. Okay? If the query does not complete, that get does not complete within 60 seconds, what we'll do is we'll take all the results you've built up that far, return those back to you along with a continuation token. And then you'll need to do the same query again, passing in the continuation token, and that will continue the query where it left off. So you need to be aware of continuation tokens when doing your queries, especially the longer queries. The last thing I want to talk about with the tables here is that since we actually have a flexible schema, the way some people are actually taking advantage of that is they're actually storing different entity types in the same table. And the way they do that is they actually have, as part of the row key, the kind type. So going back to our customer example, we could actually have a customer entities and order entities and order detail entities with those 3 different kind types. And so we could have 3 different kind types as part of our row key. And we might have the partition key for all those to be the customer ID as I went through in the prior example. Now, the benefit of this is that when we do have entity group transactions, that will allow you to do transactions across all of these entities. Now, one thing that you need to realize in doing that right now is that it does require a little customization on your side in terms of deserialization of those queries. So when you deserialize, you would have to look at the kind type that's in that row key and then deserialize to the correct object. And we are looking at future ways to make this more seamless so you actually don't have to do that custom deserialization. But you would have to do that if you want to try to do this right now. OK, so in summary, for Windows Azure tables, the goal here is to provide this massively scalable, highly available, durable structured storage. And we really focus on having this automated load balancing via these partitions. So we monitor the behavior of partitions, and we spread them out over our storage servers to meet the peak traffic demands for your table. It's provided with very simple and easy to use programming interfaces. And one important thing I wanted to emphasize here is that this is not a relational database. So we're not have no plans of supporting joins or auto maintenance of foreign keys, et cetera. The focus here is highly scalable, easy to use tables. If you need relational database capabilities, the solution for that for the Azure platform is SQL Data Services. They're focused on providing scalable relational database in the cloud that exposes SQL. And the two key features I've talked about for Azure tables is entity group transactions and secondary indices. OK. So now I want to move on to talk about queues, which provide reliable delivery of messages for your application. Well, shown here is a standard pattern for Windows Azure. When you build a Windows Azure application, you can have web roles, and worker roles. And the way you might use this is you might have a web role that takes incoming requests from the internet and then queue up work into the Windows Azure queue for some worker roles to consume. And the advantage of this is that this allows you to scale your worker roles up and down based on how much incoming work you have. And the queue provides a reliable delivery of messages for these web role to the worker role. So the Windows Azure queues provide this reliable delivery of messages. And we have unique programming semantics that ensure that a message can be always processed at least once. And I'll get into details on that in a few slides. The queues are highly available, durable, and performance efficient. And everything is accessible via REST with a very simple to use REST interface. So in going through the data storage concepts for queues, we have our standard picture here where you have your storage account. A storage account can create these queues, and you put messages into the queues. So assume Sally wants to create a queue that basically will convert pictures to thumbnails. So she may have a thumbnail job queue. And in the message, she may have a HTTP link to the original picture, as well as the size of the thumbnail that she wants. Okay, she also might have a photo processing job queue, which does things like red eye reduction or things like that, and pointers in the message to the pictures that she wants to process. Okay. Now let's dive into these in a little bit more detail. With your storage account, you can create as many queues as you want. These are scoped by the storage account name. Inside of a queue, there's no limit on the number of messages you can store, but there is a limit on the time and length of time you can actually store a message. And the reason for this is that the queue is not meant to be a long-term persistent storage vehicle. If you want long-term persistent storage, that's for using Windows Azure tables or blobs. Okay? So if a message is not used after a week, it's basically automatically garbage collected. Shown here is the URL for accessing queues, where you have your storage account. The queue keyword indicates to us that you're accessing the queue store, and then the queue name. You then specify for messages a message of up to 8 KB in size. If you want to store a message larger than that, you would store, for example, your pictures into a blob, and then store a pointer from the blob into the message. So the message would have a pointer to the blob. Now, the programming API that we have is a REST-based API. And here's a semantic list of the operations provided. It's very easy to use. You can create a queue, delete a queue, clear queues. You can actually inspect the length of a queue. And then for messages, you can enqueue a message into a queue. When you dequeue a message, you actually specify what's called an invisibility time. And what it does here is that when you dequeue a message from a queue, it returns the message along with the message ID, and it makes the message invisible for a given length of time t. Okay? And you have, within that length of time, to effectively delete the message. If you haven't deleted the message within that length of time, the message will become visible again for another worker to then consume it. Okay? So let's go through that in some detail. So assume we have these two web roles that are producers, and they produce messages into this queue. They've produced, so far, 4 messages into the queue. We do then have 2 consumers who are workers who are consuming messages from the queue. So consumer 1 comes along and it says, okay, dequeue me a message and make it invisible for 30 seconds, because I think I can actually finish processing that message within 30 seconds. So when it does this, it'll go to the queue, get the message 1, the first message there, dequeue it, start processing it. Then the other worker, consumer 2, comes along, and it does a dequeue, and it says, well, I think I can complete my processing also within 30 seconds. Well, since message 1 was invisible, when it dequeues the message from the queue, it'll skip over that, it'll see message 2, take that, and start processing it. Well, let's assume that worker 2 or consumer 2 is very fast at processing this message 2, so he finishes consuming that. Then the next thing he wants to do is do a delete message on to that queue. So he does a delete on that queue with message 2. That'll go to the queue and delete the message. And now, let's assume that consumer 1 is still processing message 1, but before it can actually complete the processing of the message, it crashes. So that worker crashes, and we've processed part of that message, but not the whole thing. So what the semantics we want is we want another worker to pick up that message and to start processing it. Well, what do we do here? Well, after 30 seconds from the original dequeue, that message will become visible again for any other worker to take it. So if consumer 2 comes along and says dequeue here, it would actually dequeue that message, start processing it, and then that message is fine. So we can hopefully process that message and get the results that we want. Now, the advantage of this is that it ensures that every message can be processed at least once. If you have a worker that crashes like we here with consumer 1, the message will become visible again for some other worker to see the message and to start consuming it. Now, there's a few things I want to point out here in terms of best practices with queues. And one's related to this scenario right here, which is a lot of applications, when they use queues, they want to make a processing of their messages to be idempotent. What that means is if I process that message over and over again, I should hopefully get the same correct result. So going back to this example here, we got halfway through processing message 1 with consumer 1. It crashed. Then consumer 2 later picked up message 1 and potentially started processing it from the beginning. And hopefully we still get the same correct result. So you want to try to build your application where processing your messages are idempotent. But you can process your messages in different ways. If you do want to try to keep track of how far a message has been processed, you'll have to keep track of that via maybe tables or some other mean. Now, the next thing I want to talk about for best practices is that there's really no fixed ordering for the dequeue of messages. Okay? We try to approximate a FIFO order, but due to this invisibility, you may get the messages back in a different order in which they were consumed. And finally, for the queue length, you can actually inspect the queue length for your queue, and this is actually very valuable for scaling your workers. Now, if you have this sort of web role and worker consumer pattern for your application, what you can do is you can look at the queue length for the queue between the two of them. If the queue is pretty much always empty, well, that means you have enough workers to process all the work that you're doing. Okay? So maybe you can scale back the number of workers you have. If the queue is always overflowing, then it sort of means that, well, maybe you don't have enough workers to keep track of all the incoming work. So maybe you need to add more workers. So a lot of applications are using this queue length to figure out how to automatically scale up and down their workers for their application. So putting all these storage concepts together, we have the following. With your storage account, you can create blob containers. In those containers, you can store blobs. You can create, with your storage account, tables. The tables hold entities, and the queues hold messages. And then shown here are the URLs, the standard URLs for accessing the blobs, tables, and queues, where you have your storage account, then the keyword for the different type of storage you want to access, and then whether you're, the name of the blob container, the table name, and the queue. So the way we differentiate which of these storage abstractions you're accessing is by this keyword. Now, this also means that the namespaces are actually separate across these. So you could actually have a blob container named music, an entities named music, and a messages named music. Okay. So the key takeaways that I want to help you go away with is, for Windows Azure Storage, this provides you as an application developer to take advantage of the vast amount of storage that's in the cloud. Okay? So it allows you to access storage that's massively scalable, durable, available, with anywhere, anytime access, and it automatically scales to meet your peak traffic demands. And the key thing here is that you only pay for what you use and store. So you don't, as a customer, you actually don't have to build out the infrastructure and over-provision your data center to try to meet that peak traffic demands. You basically can leave it up to the Windows Azure Cloud to meet those traffic demands, which can save you a similar amount of cost as well as time and energy. Then in terms of the data abstractions we provide blobs, tables, and queues, and these are provided with very simple and easy to use REST and .NET interfaces. And this is all available right now via CTP access. You can go to these websites, get access to this, start playing with this. You can download the SDK. There's forums, white papers, and additional talks. Our technical evangelists put together this Windows Azure application, hooked it into Twitter. So if you do have feedback on the talk or questions, you can Twitter at TWEval and specify #WA storage and enter any message along with a number. And he said he's going to do something with that and surprise me. And it'll appear at that website. But if you want to send me messages or send messages about the talk or ratings of the talks, do send them there or our forums. There were 2 talks yesterday at MIX, an overview of Windows Azure, as well as Steve Marks gave an example of building applications on Windows Azure. Those should be online today, as I understand it. And there's another section on Windows Azure tomorrow at 9:45 in San Paulo 3401. And last thing, make sure you fill out the evaluations that are in your seat and turn them in at the door when you leave. And thanks. So if you have any questions, there's Mike.
Thanks, Brad. Quick question. If a customer asks you regarding security and what kind of issues are there, besides kind of encrypting it yourself up in the cloud, is there any options there? And how would you respond to such a question?
I don't know if the mic volume can be turned up. I heard the question, but it's sort of faint. So the question was about security. I heard the question. For accessing storage, all authenticated requests are basically signed for secure access. You have the choice to use HTTPS or HTTP. HTTPS will be more secure for you. But if you use authenticated access, that's basically our security model for accessing the storage system.
Hi, Brad. Just a quick one on the naming for Azure Tables. There's quite a few people who I've spoken to who think that perhaps Azure Tables isn't the correct name because they're not really tables. It's more entity storage. I just wonder if you're taking that feedback on board, whether there might be any changes because of that.
Oh, you mean, yeah, it's actually, the name that we're going with is Windows Azure Tables. We've had a few feedback like that, and it's up to the business folks to figure out what they want to call it.
Okay. So you don't care?
They do have the business fact. What?
So you don't really care?
I'm an engineer, you know.
Yeah, that's what I mean. Okay, thanks.
But we have gotten that feedback, but thanks. Yeah.
Hi, good morning, Brad. Could you mentioned SQL data services briefly. I guess for building an application, you do typically need relational access. I mean, either we go with a smart kind type in the key as you mentioned, or we actually would like to use truly relational model. Could you contrast like if we are building an application, should we use both of these or one of these or?
Well, one thing in mentioning that we actually have these two storage offerings, you can actually use them together or separately, and they all work with Windows Azure. So if you do need relational database capabilities, you should be using SQL Data Services because that has the full relational database capabilities and the SQL semantics. For some applications, they just need this, highly scalable, simple tables effectively with these entities, and this is enough for them for their application. So it's really up to your application on which which will suit you.
And my second question was on blocks. You mentioned you can actually put a hash on the blocks, and when you get them, you can actually check whether the blocks are correct or not.
Yeah, so that one slide I went through, sort of a verbal description of, you can actually, that block ID, you can actually put whatever tag you want in there. So you can actually treat it as whatever metadata you want. So what some applications are doing is, for the block ID, they're actually using that as a unique hash of the data block contents. Then they're downloading the block list first, and then doing range gets on the blocks, and they have the block IDs, and they use that block ID to do the MD5 or whatever data integrity check they want.
But I thought when you do a get, you do it for the whole blob. You cannot do it for the blocks. So sorry for not explaining that clearly enough, but when you do a get, you can do two things. You can do a full get, or you can do a range get. You're right, you can actually do block gets, but what you can do is you can get the block list. From the block list, you know the ID and the size of every block. And so if I'm doing a range get of 1 megabyte to 2 megabytes, I know in the block list where I am, and I can do the corresponding data integrity checks.
The question that I had is, do you see the blob storage especially like being a key going towards a CDN type of an offering, like a type of an Akamai competitor or something to that? Because that's one of the areas where we're looking at and saying, is this something where Azure can help us in that space?
Yeah, we are looking at hooking the blob store more seamlessly into CDNs. So right now, you can actually take the blob store, make your container public, and actually just sign up for a CDN and just start using it that way. But we are looking at hooking it more directly into CDNs to make it easier to use. Yep, that's a good question.
Okay, excellent. That was going to be my question too. So I did have an expansion on the geolocation piece. You did mention that we can now pin Azure storage to a specific area, right? US North, Midwest, whatever the case may be. Is that like a single instance, or can we pin it to different areas around the world? Can you expand a little bit on the geolocation piece then?
Yeah, so for now, one thing I didn't have time to go into in this talk is the replication story for Windows Azure Storage. Right now, we replicate within a geolocation, and the way we replicate is we replicate your data 3 times. And they're replicated over fault domains and upgrade domains. So if a fault domain happens, these have redundant power, redundant networking, and if a fault domain goes down, we still have 2 healthy replicas to serve your data from. Now, for right now, this is all done within a given geolocation. So when you associate your storage account with a geolocation, that basically is where the data will be replicated for its durability with redundant power, redundant networking, et cetera. In the future, we will have what we call geo-replication, which will then allow you to replicate your data across geolocations. But that's not available at this time, but we are working on that.
Hey Brad, my name's Sean. I've been trying to build an Azure application, and I think I've encountered a bug with table storage when you're trying to insert a string of more than 1,000 characters. Is that something that's known? Because the documentation seems to indicate that I could do 64 kilobytes.
So for a given, so which property are you referring to, or the URL?
Just an arbitrary field within a table.
Yeah, so for one of the properties, right?
Yeah.
Yeah, it should be 64 KB. So if you send me email or post on the forums, we'll definitely look into that because it should be 64 KB.
Okay.
I think that only happens to use the local SQL.
Yeah. Yeah, okay. So one thing to mention there is that we do have this SDK which allows you to run everything locally on a box, and there are a few semantic limits in terms of the size of some of the fields that you can do locally versus in the cloud, and that's probably one of them.
Hi, my question is a combination of a couple of the other ones earlier. We're really interested in using your storage for delivering of media. Now, you can have a REST request which has a byte range in it. Do you also honor the standard HTTP 1.1 byte range? So if players like, let's say, Flash player or iPhone, I know, dirty word, do quasi-streaming this way, where they go and actually do byte range HTTP 1.1?
Yeah, for GETs, we do support the standard byte range. So you can actually stream by getting the whole blob or just getting a specific byte range. And if there's a connection issue, you can just continue where you left off doing a get by that range. And that, yep.
Hi. So if I am to go to my boss and pitch the idea of using tables to store data, I know the first question he's going to ask me is, so how fast are the searches? If I've got a couple of million entities, how quickly can I find one? Do you have some sort of anecdotal evidence that I can provide?
Yeah, it really will depend upon your schema and your exact queries. Inserting entities and dealing with entities, it's millisecond operations. Right now, for querying over entities, it really depends upon whether you're querying over a partition key or not. If you're querying over an exact partition, then it's depending upon how big that partition is, it could be a few hundred milliseconds. If you have to query over a whole table with millions of entities because you're not using a partition key, then it will take longer. Once we have the secondary indices, that'll make the querying over non-key properties, very fast.
So is it fair to say that for if a query is well indexed or using the index as well, that it's comparable to a standard SQL query?
Well, if you look at a standard SQL box, they're not doing, they're not replicating 3 times, et cetera, et cetera. So it will be slower than a standard, SQL one instance box. The best thing I advise is really to, do a little prototype and play with the latencies. And one thing is, we are still in CTP. The target is to go commercial release by the end of the year, and we will have significant perf improvements by the commercial release too.
Okay, thanks. Okay.
I've got a customer that we've got to send a large amount of data to on a biweekly schedule. It's about 10 gig of data that we're piling up. And I was talking to a tech evangelist yesterday, and he was saying, well, why don't you just use blob storage? You can just post the file up there and go ahead and grab it down. But it doesn't look like it's that easy. So I'm assuming, do I have to write a web application or some application around this to get that blob down or post it up? Or is it really that easy?
Yeah, we do have... and I forgot the name of it, but I think it's called Azure Drive. So with the SDK, there's like an Azure Drive application which you can actually just use to basically access your cloud storage blob account and just plop files in and out, just like a folder in Windows. So we do provide some simple things like that, and I expect over time there'll be more and more, as the community grows, more tools like that to allow people to easily use without having to actually programming those sort of tools themselves.
Now, is that the Azure Drive that's only available to the person posting the file? Or could you also use that to retrieve the file?
Anybody can run it on their machine as long as they have access to that storage account with the secret key. They can get and put the files from there.
Okay, and I guess that's available from the Azure site.
Yeah, it's part of the SDK, I believe.
Okay, thanks.
Yep. Okay, thanks for coming.